Okay, I can see very few participants. So good afternoon, everyone. Wishing you all a very happy 2026. I hope your vacations were good and you enjoyed them and you were also in touch with your whatever lectures we have gone through till now. So, just to recap, before I start today's lecture, we have what we have studied till now in this device grade materials or important materials part 2. We have learned about first thing was the semiconductors, the band theory of semiconductors. What are the different kind of semiconductors we have? We have the elemental semiconductor like silicon, germanium. We have compound semiconductor like gallium arsenide. So that was what we have learned in the first lecture. Next two lectures were mainly on the growth of single crystal of this, mainly of these semiconductor materials like silicon and the growth theory and how these are made industrially. Like we saw the Zekrolsky technique and float zone technique for gallium arsenide and silicon mainly. Then we went on to the thin film depositions. So different thin film deposition techniques which are used like thermal evaporation, physical vapor deposition, basically PVD and CVD. So in PVD, we learned about the thermal vapor deposition, electron beam deposition, sputtering, we have learned about that. And in the chemical vapor deposition, we learned about the different techniques for like how we are using silane and all those things can be done. And then these were the first four lectures. Then the fifth lecture, that was the last lecture we had on 19th of December, was on the thermoelectric materials. So how the thermoelectricity is generated, what kind of materials are required, and what are the different techniques of making them, making the thermoelectric materials, and how a device is made, how they are connected, all the challenges which are there in the making of thermoelectric device. So we have till now covered this part. So today, the part which is remaining, the last of my lecture is the photovoltaic materials. So before I start the photovoltaic materials, so let me know if you all are having any doubts, and then so just 1 or 2 minutes before I go into the photovoltaic materials, tell me about how you are feeling about this these lectures, and if there is any doubt or anything, just let me know, and then I will start my presentation. Hello, are you able to hear me? No response? Okay, lecture notes are not loaded. I will check with the IT team and find out what are the issues with loading the lectures. But which is the last lecture you can see the notes? No response. Somehow. Last two lecture notes are not loaded. Okay. Okay. And so none of you have got any problem with whatever we have been covering, right? So should I start then? So, okay. So functional materials part 2, I will be starting with the photovoltaic materials. So photovoltaic, huh? So this has got two words. Photo means photons, light. and voltaic is the electricity. So basically, photovoltaic materials are the semiconductor devices that convert sunlight to electricity, as the name suggests. So a solar cell is the basic element of a photovoltaic module. So this, which I have shown here, is the solar cell. So this, we will be studying more about the solar cells today. So what are the different materials, how a solar cell is made, what are the different materials, and what should be its property and related to it. So what is a solar cell? What is a photovoltaic module? So solar cell is the basic element of a photovoltaic module, and the generated power using this solar cell can start from milliwatt, which is used in a calculator. No? Normally, you must know that our small pocket calculators, they are also working on the solar energy, or to few megawatt also. So when we have got a very big solar plant, you can generate energy up to megawatt, like a power generation. So here I have shown a basic photovoltaic cell. This is how it is. So we have got a semiconductor here. This layer is semiconductor. Then we have got some anti-reflective coating. Then we have got electrodes here. And then when the sunlight is falling on this full thing, then we can generate electricity. The light will start glowing. So how it is that in our last lecture, you remember that we had the thermoelectric materials, we were having a temperature difference. The one end was at a hot temperature, one was at cool, and because of that their EMF was generated, and then because that EMF was leading to the production of electricity. Similarly, in this case, it is just sunlight which is falling on a semiconductor material, and we are able to generate the electricity. So how does it happen? So before going into that, the first practical solar panel was demonstrated in 1954 by the Bell Labs. So here is, this is just a pictorial. So like Bell system solar battery converts sun rays into electricity. So that is 1954, and it was in the laboratory. But now you know that most of our rooftops are now converted into solar cells. We have got solar photovoltaic modules are there, and this is a part of the green energy and zero emission, zero net zero. So because of its very renewable energy and no emission or no pollution, so solar photovoltaic cells and solar energy has come up largely in the last few decades. So here I am showing you that it starts with the solar cell. So this one piece is called the solar cell, and this makes into a solar module. So this is the solar module, and then many such modules make the solar panel. And this panel, when we are generating electricity, so we should have a solar panel, and many solar cells are joined together to make the solar panel, so that how much electricity you want to produce. So depending on the kind of electricity, whether it is a milliwatt or megawatt, so number of solar cells increases, and these are all are joined together. So what are the advantages of the solar cell? So first thing is, like I told you, this is renewable energy. The sun is the perpetual and the most abundant source of energy on our planet Earth. And if we can convert that energy to a useful electricity, so that nothing good other than that. So solar energy is a renewable energy source. Then we have got clean and non-polluting. There is no emission coming out from it. Then high power to weight ratio. The solar panels are very light. The photograph you were seeing earlier, one cell is just like 300 micron thick. So it is very less weight, but you can get high power from it. Easy installation, and you don't require maintenance after installation also. Just you have to clean it. It can work. no fuel cost or no fuel supply problem. You don't have to give any input to it. Input is sun. Then you have got long operation life. Then it does not produce any noise, or it can be used in a remote location, in sea and in space, and there is no waste material coming out of it. So because of these advantages, like all our missions, space missions, so the energy for the space missions are for coming from the photovoltaic cells, the solar energy is used. But obviously, it has got some disadvantage, like solar power cannot be obtained at night time, and panels are relatively expensive. We will be coming to that part. And energy has to be stored in batteries. It is not like, it is not plug and play. You are getting the solar energy, just you have a panel and you can just light your bulb and work in the household. It has to be stored in battery, and from the battery you can use it. Then if you want to produce large power, so you need large area of land to produce more efficient power, and issues with tilt and alignment of panel. So the photovoltaic panel should be facing the sun. Otherwise, maximum energy you cannot, maximum power you cannot take out. And if it is a very large plant, you have to maintain the surface of the solar panel so that the sun energy is properly absorbed. Now, when we talk about the solar energy spectrum, so at a given time, the light intensity on Earth's surface is about 70% of the intensity above the atmosphere. So if this is like the sunlight at the top of the atmosphere is around this, and whatever we are getting at in our atmosphere, so this much is getting absorbed. So this curve is this is like a black body spectrum for a 6000 degree centigrade, but radiation at sea level is very less. So this is and at higher wavelengths, because of the scattering, so the radiance of the, or the intensity of the sunlight keeps on decreasing. So absorption and scattering effect increases the sunbeam path through the atmosphere. So as we all know that during sunset and all, or sunrise, so because the sun rays has to travel longer distance, so more and more scattering is there. And the spectral distribution, or the air mass 1. So here I have said it is called air mass 1, and this is air mass 0. Air mass 0 means at the top of our above the atmosphere of the earth. So that is air mass is 0. Air mass 1 is the when the sun is just at the top. So when the sun rays are traveling through our atmosphere, there are many sharp absorption peak. You can see here, like this is H2O absorptions are there. So, and CO2 absorption are there. So many wavelengths are absorbed by various molecules in the atmosphere, such as ozone, air, and water vapor. So these wavelengths do not reach Earth, or their intensity decreases when they are reaching Earth. So here is the concept of air mass. So as I told you, air mass 0 is the at above our Earth's atmosphere. So air mass refers to the mass of air with respect to vertical height of atmosphere that light has to travel from sun before reaching ground. So on a sunny day, light intensity on Earth's surface is about 70% of the intensity above the atmosphere. So the solar constant, no, that is the intensity above the Earth's atmosphere, that is air mass 0. The total intensity above Earth's atmosphere is approximately 1.35 kilowatt per meter square. This is around 135 milliwatt per centimeter square. So that is the intensity of the solar energy above the Earth's atmosphere. But when it reaches Earth, so it can be either coming straight, the sun can be just above. So this is the air mass 1. But generally, if at a given time there can be some directional. So this phi, if phi is around 48 degree or 50 degree, so it is called air mass 1.5. So at air mass 1.5, this 135 milliwatt per centimeter decreases to 100 milliwatt per centimeter square. So the geometry of the relative position, amount of incident radiation depends on the position of the sun, and the geometry of the relative position of the sun and the inclined plane of the photovoltaic module used to simulate a standard distribution of solar radiation. So our module can be tilted like this as respect to, so that it is directly coming. So generally you have seen that solar modules are not like sun, they are not exactly horizontal, they are kept at an angle so that maximum time they have a air mass of 1.5. So this angle, this is from your solar mass is here. So whenever this is, this is around 50 degrees centigrade. So we get around 100 milliwatt per centimeter square at a given time on earth. Now this is the incoming radiation, incoming energy. So, and from this energy, we have to find out, we have to take out the electricity. So as we have just now discussed that photovoltaic is solar energy conversion into electrical energy. So a photovoltaic solar cell is made up of three main parts. A light absorber, so you have to absorb the light. So this part converts the incident photon into electron and hole pair because they are made of semiconductors. Then what happens? This there has to be a carrier or a collector. So this carrier or collector region, what it does, it captures the and carries the electron and hole. So whatever electron and hole are produced, they are now carried forward, and metal contacts are used to carry forward it to the circuit so that it goes to your load. Whatever load is there, so this metal contacts take it to the load so that the circuit is complete. Now, in case of a photovoltaic cell, so it is a semiconductor. But what kind of semiconductor? What kind of junction? So it is made of a PN junction. PN junction with very narrow N region. So N region is very narrow and the light enters through the thin N side. And the electron hole pair is formed in the P-type semiconductor. So how does it look like? So this is a typical schematic of this is a solar cell. So PN junction with very narrow end. So this is the N part and this is the P type. Okay, here is the N and this is the P. And now we have the base, P, N is the emitter, P is the base, and we have to take out. So electrical connection is taken from this side. Okay, the elimination is through the thin N side. So the photons are coming through this. The semiconductor layer extend mainly in the P region with built-in field. So because this is a PN junction, so we have learned in the first chapter that when there is a PN junction of a semiconductor, there will be a depletion layer, and on the two sides of the depletion layer there will be a electric field because of the either like cations or anions, buildup of cations or anions. So there will be some built-in field, and electrode at end side must allow illumination to enter the device. So these electrodes are there, these are the metal electrodes. So because our photon is entering through the N side, so they are like very thin, and this electrode is an array of finger electrodes. Now you can see how it is happening. So just see this animation and then I will describe. So in this animation, you can see that these photons are coming, right? These photons are coming and they are falling on the p side, which was the p side, p type semiconductor. And because of that, this we have got holes and we have got electrons. So then these electrons, these are the electrodes. The electrodes, through the electrodes, the electron will start flowing. So we have got photons coming, the electron hole pairs are generated, then we have got the contacts, the front contact and the back contact. The electrons and the holes will be flowing through the through the outer circuit, and thus this bulb is glowing. We are showing it here, like the circuit is completed and we see the electricity. We develop the electricity. So this is basically how a photovoltaic cell works. So this is how the semiconductor is converting the photons into electrical energy. Okay. Now, if we see in terms of band energy, band gap, how things are happening. So we have a N-type semiconductor here. This part is the N-type. We have the N-type semiconductor. This part is N-type, and this is P-type. Okay. And we have got metal contact. So this is metal contact. This is metal contact. And this is the Fermi energy. Now photon has come and it has fallen here. So what happens when photon comes? We have a photon is coming and falling on the p-type. So we have got a hole in the valency band and an electron in the conduction band. And they start flowing. And because of that, we will get the electricity. So as we see that we have N-type, we have P-type because of that, and we have got this E0, the electric field, because of the anions and cations. And when the radiation is falling, we get an electron hole pair and which conducts electricity. So basically this PN behaves like a forward biased PN junction under illumination. So we are generation of voltage in the PN junction. And what happens, how it is working. So this is the here we can see the IV characteristic. So this is you can see this first part is the how dark this is the diode IV. So a PN junction in the dark consumes power and it can be operated in the first or third quadrant. This is how this is the IV characteristic of a normal diode, PN junction. So effect of solar radiation on the IV curve is normal dark current characteristic being shifted down by photocurrent IL, which depends on the light intensity. So this curve has shifted here. This curve shifts here. So this shifts here. So when it is under illumination, means the photons start following, the diode characteristic remains same, but only the values changes. So even at the given voltage, we have got current. So this is like even at a zero voltage, we start getting some current. So this at zero voltage, this current is called the short circuit current. This is called the short circuit current. And under illuminations, solar cell can be operated in the fourth quadrant. So this fourth quadrant is the operating. This is the operating region for a solar cell. And when it is operated in this fourth quadrant, it is corresponding to delivering power to the external circuit. So operating diode in the fourth quadrant generates the power. So we are getting I and V. Current in the illuminated solar cell is negative, so flows against the conventional direction of a forward bias. The open circuit voltage is given by the point where the IV current cuts the V axis. So this is the, and when current, this is called the open circuit voltage. We'll be coming to that. So we have got two main parameters. This is short circuit current and this is the open circuit voltage. What does they mean? So now we are just looking into the fourth quadrant. Huh? This is now just the fourth quadrant. Okay. We have got this voltage. This is the current. So this is the open circuit voltage and the short circuit current. So basically what does this open circuit voltage and the short circuit current means? These are very two important parameters of a solar cell. So the short circuit current means that is the maximum current which you can take out from a given solar cell. So if it is shorted, there is no load. So what is the maximum current? So that is the short circuit current. And what is the load? If there is open circuit voltage. So if there is no current flowing, so what is the voltage? That is the open circuit voltage. And what is the maximum power you can? So we have got the open circuit voltage and now P max is the maximum power point. So this is the maximum power point and the corresponding current and the corresponding voltage with respect to P max is the maximum voltage and current. So PM is the maximum power point and IM and VM are the maximum power and the voltage point. And this, there is another factor called the fill factor. So it is measure of the closeness of the solar cell IV curve to the rectangular shape. So now this is the full working area you can operate. So this is the maximum I, this is the maximum V you are able to take out from a given solar cell. Now this part, because this is the V max and this is I max. So actually you are not able to operate it in this region. Your operation of region is only this much. So that is called the fill factor. So it is the measure of closeness of the solar cell IV to the rectangular shape. Actually, this IV to the rectangular shape. Now coming to the efficiency. How the efficiency of a solar cell is defined. So efficiency is the amount of the input power to the amount of the output power. So if P max is VOC means open circuit voltage into short circuit current into the fill factor. This is the P max and P in is the solar power. So like 100 milliwatt per centimeter square. So this is the efficiency of the solar cell, of a given solar cell. And fill factor is defined as I max, V max upon ISC upon VOC. So these are the different parameters how you define a solar cell. So whenever you are working on a photovoltaic material, you are fabricating a solar cell. So these are the values you have to quote and compare with what is commercially available and what is achieved by world standards. And we have to, so basically this efficiency, this parameter should be more and more. So we come to the operation of a solar cell. So generation of light generated carrier, if radiation with photon energy greater than the forbidden width, because we have to EG, no, energy gap. So because electron hole pairs are forming, so the energy of the photon has to be more than that. So the choice of material becomes important here, that we should be using those material only for whose the energy gap is less than the energy of the photons of which are coming from the sun. So it is absorbed and this energy is used to excite the electron from the valency band to the conductivity band. The electrons drift and reach the neutral inside, whereupon it makes this region negative by amount of charge. The hole drifts and reaches the neutral p side and thereby make this side positive. This is called as the open circuit voltage between terminals of the device. If there is an external load, electron will travel through it and recombine with the excess holes in the p side. If the terminals are shorted, then the excess electron in the inside can flow through the external circuit to neutralize the excess hole and this is current is called the photocurrent or the short circuit current. So collection of the light generated carriers to generate a current, and generation of a voltage across the solar cell and dissipation of power in the load and parasitic resistance is the main point of operation of any given solar cell. So you are able to understand this much? No problem? Any problem till now? No? Okay, then I will just take a 1 minute break and then we will come back. Okay? Okay, we will continue. So the first question of today is like, uh, if we are choosing any material for making a solar cell, so what is the band gap of the material should be? Like what kind of band gap material we will be looking for to making a photovoltaic cell? So whether it should be like 10 EV or say 8 EV or maybe 5 EV or say, so what kind of band gap material we should be choosing to make a photovoltaic cell? Okay, got the question? No issue, na? So I will go forward. So now basic structure of a photovoltaic cell. How does what is the structure? So we know that it should have a P region, it should have a thin N region, but how does it really work? So we have in the photovoltaic cell is made of three main parts. So light absorber, carrier collector and metal contacts. So, and the heart of the solar cell is the absorber layer. So we have this is the absorber layer and this is the p-type semiconductor. Above that we have the n-type semiconductor, which is the thin part, and this is the p-n junction. So because of the p-n junction we will be having a electric field across it. Above the end there will be a front contact because ultimately we have to make a circuit. Okay, so there will be some load and across which we can that our bulb will be glowing. So between the front contact and the back contact is required. Then we have got an anti-reflection coating. So why this anti-reflection coating is there? Because to have maximum efficiency, so that more and more solar photons which is incident on your given cell is absorbed, because you know when a photon is incident on any given material, so it can be either like transmitted or absorbed, and there will be reflection also. So reflection losses can be minimized by using anti-reflective coating. And for passivation, we have a glass cover. So this is the basic structure of a basic schematic of a photovoltaic solar cell. So, and the current is between the front contact and the back contact. Now, depending on the use of material, what kind of semiconductors we are using for making the solar cells. So the solar cells has been like tabulized in three generations: first generation, second generation, and the third generation. So first generation are the wafer based, and they are generally silicon. So they are silicon based. So silicon cells are used, silicon. So wafers like this, whatever we see now commercially, they are all still the first generation solar cells, and they are made up of silicon wafers. So we have got, so they can be silicon, can be both monocrystalline, means single crystal silicon can be there, or polycrystalline. So both can be used. And the efficiency for monocrystalline silicon is around 25%. And polycrystal, because there will be grain boundaries, there will be scattering of electric charges. So for the polycrystalline, the highest efficiency is around 20%. But this is increasing day by day. Then we can have multi-junction cells, like different band gap material. We can use gallium arsenide and all those things. So using them, we can have a very high efficiency of 40%. Then came the second generation of the solar cells. So these were based on thin films. So why to go to thin films? Because they are cheaper. You don't require a big single crystal silicon. Uh, so there are many advantages. So, but what was the semiconductor which has been used in this? So amorphous thin films of silicon were used. Then cadmium telluride is there. Then copper, indium, gallium selenide. This is one of the highly used semiconductor, thin film semiconductor, which were used. And for amorphous silicon, the efficiency was just 13%. Then there was, for the cadmium telluride, it was around 17%. And this CIGS, copper, indium, gallium selenide, is around 20%. So they are made on like this glass substrate is there, and then the films are deposited and contacts are taken. Then came the third generation, and work is still going on. So these are like dyes are used, and we have got organic semiconductors, they are used. So they are like dye sensitized solar cell, quantum dot sensitized solar cells are there, organic photovoltaic, which are like polymers are used. And then hybrid solar cells are there, where some inorganic and organic, both kind of semiconductors are used, and perovskite solar cells. So in the coming few slides, I will be describing all this, their basic structure and working for the first, second, and third generation of solar cells. Before going into that, we should know the efficiency and different characteristics of this different kind of solar cell. So we are like comparing single crystal silicon. We are having cadmium telluride and CIGS, copper, indium, gallium selenide, and perovskite. So this is first generation. These two are second generation, and this is the third generation. So if we see in terms of raw material cost, so raw material cost is low for cadmium telluride on silicon and perovskite, but slightly higher for CIGS, because you are using copper, indium. These are high purity materials. Rare earths are there. Then finished material cost, when we come now after making the photovoltaic cell. So if we see, so for the finished material cost, the cost for single crystal silicon, we know that making a single crystal silicon is very costly affair. So it is very high, and similarly for CIGS. And fabrication cost also for single crystal silicon is high. Then we have got energy payback period. Energy payback period means when the energy, whatever cost we have put for making it, and when we start getting energy. So what is the time? So energy, because the initial cost of like silicon, single crystal silicon was very high. So energy payback period is also high. So generally it is directly proportional to the material cost. Whereas for perovskite, we'll see that these are very low cost material, making also very easy. We can be using methods like thin film deposition, spray painting, spin coating. So that's why all the cost of this material is low. Then comes the LCOE. LCOE is levelized cost of energy. What is levelized cost of energy? It is the total lifetime cost, which includes building, operation, and decommissioning of a solar project divided by its total energy production. So basically, it is the average minimum price per unit of electricity. How much we are paying per unit of electricity to get it. So it is low for perovskite, but for both CIGS and for silicon, it is high, and medium for cadmium telluride. But when we come to efficiency, we see that silicon based are highly efficient, and now the third generation of perovskite based silicon solar cells are also having high efficiency. So that's why, that is the reason for which this perovskite materials or the third generation solar cells are becoming more and more important, and more research is going on. However, they have started coming up commercially, but still a lot of research to make them more stable for large area is still going on. And if we compare the efficiency of these material, worldwide efficiency, these are few tables I have taken from different sources. So like if we see silicon monocrystalline cell. So this is, the first one is cell, means one cell, and this is for one full module. In the first slide I have shown what is a cell, photovoltaic cell, what is a panel, and what is a module and a panel. So and this is the area. Okay, so we are talking about the area. So the efficiency for a single cell of silicon monocrystalline is around 26%, but when it made into module, it decreases to 24.4 or around 25%. Multicrystalline silicon is around 19.9. So I have written that now. This I have written as 25%. This was around 20%. Now for CIGS cell of 1 centimeter square, just 1 centimeter square, it has got a very high efficiency, 23.4%. But when we make it into a module of area of 841 centimeter square, its efficiency decreases to 19.2. For a cadmium telluride cell, it is around 21 and 19%. And for a perovskite cell, for a module of 802 centimeters square, this has got a efficiency of 16.1. So why this area, no, why I am talking about area and all, and why it is important is that because we are trying to harvest the solar energy. So we require high area, no, large area. Panels has to be larger and larger area so that you can absorb more and more solar energy. So that's why it is the, so when you are connecting more and more cells, so there will be some parasitic resistance, some electrical contacts will come into place. So at those places, there will be loss of energy. So that technology is also important. So that's why we are comparing that for a given one cell, the efficiency may be high, but when you are making it into a module, the efficiency is decreasing. Now commercial use of different types of solar cells, if we see, so and now we have to keep in mind all the points which we have learned in the earlier slides, like cost of making, installation, long term, and then efficiency. So if we take into this, so we see that how the commercial use is there. So we see that 49% is multicrystalline silicon, multicrystalline silicon wafers are 49% market share goes to the multicrystalline, and next 34 is to single crystal. CZ makes silicon crystals are there. So though the efficiency of this is around 25% and this is around 20%, but because of economy, because making of multicrystalline silicon is easier than Czechoslovak crystal pooling, so they are more abundantly used commercially. Then we have got around 8% cadmium telluride and amorphous silicon. These are the thin films are there. These are all thin films. And we have got around 3% of silicon, our silicon is there, and CIGS is around 1%. So this is how the distribution. Commercially, these are available, but we don't see the third generation silicon solar cells still here commercially. Now coming to the construction of a silicon solar cell. So we have already seen that we have a p-type semiconductor silicon, then we have n-type silicon, and then we have got back electrode of aluminium and front electrode of silver and anti-reflective coating of TiO2 and passivation layer of SiO2. Why passivation layer? So that for the long term working and so that there is no degradation of the under beneath silicon. And if you see the thickness, so this p-type semiconductor, which is the light absorber area, it is just 200 micrometer. 200 micrometer is around 0.2 millimeter, right? So just thin wafer, and on that we have a very thin layer of N silicon. Why very thin layer of N silicon? Just to remind you again that it is very thin because so that whenever photon is coming, it should be able to enter this. Then we have got just 20 nanometer of silicon oxide and 80 nanometer of anti-reflective coating, and above that and below are the different metallization. So this is basically a typical diagram of a silicon solar cell. And fabrication of silicon solar cell, if you think what is the full process. So first, if we see like when we are calculating the cost and all, we should know what are the process it has gone to. So first we start with the sand. Sand is converted to silicon. Now silicon goes to ingot. So silicon to ingot. So this ingot can be both single crystal or it can be polycrystalline or multicrystalline. So we have got ingot can be both. So that is difference. Then this ingot is cut into wafers. Then these wafers, each wafers is now doped. So we have to dope this into the p-type and n-type. So phosphorus, boron, this doping is carried out. Then we have to coat it with the anti-reflective coating and silicon oxide. After that, each cell is tested. Then it is made into a panel. Then panel is laminated so that further lamination is there. Then framing and final testing and shipped. So this is the full flow chart from silicon oxide to a photovoltaic system. So how the industry works. And if we come to the fabrication, actual fabrication, what happens? This part, now we said that silicon wafer doping is there. So what happens during how the P and N layers are formed? So when we are talking about a P-N junction, so it is not that a P-type semiconductor and an N-type semiconductor and come and they are stick together. A single silicon wafer is taken and some part we have to dope with the p-type dopant and other part it is doped with the n-type dopant, p-type and n-type. So first during this process, first we have to chemical etching is there so that any impurity is there, it is etched out. Then diffusion of phosphorus and creation of a p-n junction is there. Then deposition of a passivation layer and anti-reflective layer. And then screen printing of front and back electrodes. So this aluminum and silver electrodes are there. So they are screen printed. Then metallization of cell electrodes in thermal process, and finally IV characterization. So when in this process, whole process, all these are the steps which are taken. So just a very small video I am showing from net. Only I have taken it, like how industrially it is done. So we start with the silicon, and so we are using the sand is taken. Now it is SiO2, sand is SiO2, it is converted into silicon. So we use very high temperature furnaces, and reduction of oxygen is there using different processes, carbothermal and all chemical processes also. This is a very high temperature process which takes care, and then the silicon is now grown into the single crystal. So you see this is the single crystal silicon which is taken, and this crystal is now cut into wafers because we want wafers. So cutting is there. So this is a multi-wire cutting is going on, and we get wafers. So here are the wafers are there of silicon, and these wafers. So these you can see all the wafers are there. Now this is around 300 micron. So each wafer is now polished, and all those processes are cleaned, polished, and then at high temperature they are first the screen printing is there for the metallization is there, then they are doped with phosphorus at high temperature and boron, and then they are tested. So each cell is then tested, each cell is tested, then all metallization is done, then they are all the cells are now connected to each other. So all is done in machine, so they are being connected to each other, and you can see that they are connected to make the module. So many such cells are connected. This is electrical connection is done, and then they are framed to make the full panel. This, so some coating is there, some polymer is coated on them, then frame is put on them to make the full panel. So this is like how, so this is now your final panel is there. So this comes out the panel, and then the panel is again tested, and behind the panel electrical contacts are taken. So this is one such panel which is now mounted on your rooftop or in the photovoltaic. So this is how it looks like. So we have started from silicon oxide, which is the sand. We have converted the silicon oxide to silicon. Then silicon was, here we have shown it as a single crystal growth, but polycrystalline growth can also, polycrystals can also be taken. So here this is the single crystal, and this is a polycrystal. So ingot of a multi-crystalline. So when we see that the module, the wafers after cutting, so this is how for a polycrystalline is looks. So we have got many grains are there. So multiple grains are there, and this is a single crystal. Otherwise, the processing, other processing remains the same. So this is single crystal versus multi-crystal solar cell. Okay. And in BRC also, many years this work is going on, and solar cell and modules were developed for space application. So Bhaskara 1 and Rohini 1, whatever space application, these solar cells made in BRC were used. So we have got the back contact, this is the front contact, and this started with the wafer, and full panel was made, and the technology was transferred in 1984 for making this. Now coming, so till now we were discussing about the first generation solar cell. So now we will come to the second generation solar cells, which are the thin film base. So before going into that, do any one of you have any questions? No questions? No doubt? Hmm? Okay. So just take 1 minute of break and then we will start with the second generation of the solar cells. Okay. Okay. All of you are there? No problem. Na? Till now, everything is clear. So the first question you remember, what was the first question today's? Anyone can tell me? No one is there to tell. Okay. So then I will start with the second question. Today's second question is uh, why the efficiency of multicrystalline solar cell is less than the efficiency of a single crystal solar cell. So this is simple question. Why is the efficiency of a multicrystalline solar cell less than the efficiency of a single crystal solar cell? Okay. So we have got two questions till now. Now coming to the second generation of the solar cells. So they were based on the thin film solar cells. So thin films of like cadmium telluride or our copper indium is there copper indium, germanium selenide, all those things. Or we can also use amorphous silicon layers. So in this case, the absorber and the conductive layers are deposited on a substrate because this is a thin films. And then they are separated so that they are monolithically connected in series. So they are on top of each other. The interconnection is necessary to convert high current and low voltage output into a low current and a high voltage. This minimizes ohmic power loss, which scales as a square of the current. Okay, the most prominent thin film solar cells are cadmium telluride, copper indium selenide, amorphous silicon, or silicon microcrystal, or a different combinations. Amorphous silicon with silicon, or silicon amorphous with single crystal silicon, like that. So today thin film solar cells have a market share of around 12%. The above cells are made with the method of depositing successive layer on a glass base covered with a thin layer of a transparent conductive oxide. Because these are thin films, so you require a substrate. And the substrate has to be one contact. So that's why it is generally contacts like transparent STO, no, is there transparent oxides like conductive oxides are taken. The rear contact is achieved through a thin layer of metallization like aluminum or gold is taken. The significant advantage of such cells is the possibility to produce their successive construction layer by means of such technique as chemical bath, vapor deposition, electrolysis, magnetron sputtering, or spraying, etc. So that is what makes them very cheap. So here you are not using any bulk material, but you are using only thin films. So one is that material cost is also going down and the techniques are also cost effective. So they are produced from cheaper polycrystalline material and glass, sorry, and they have high optical absorption coefficients. So, and the band gap is suited to the solar spectrum. So whatever solar spectrum is there, we can change the band gap of this material, or we can select those material whose band gap matches with that of the solar spectrum. But limitations are there because when you are using like cadmium telluride or cadmium selenide, so the longevity, the robustness of these thin films are important because you will be using them outdoor. So here is a general layout. So we have a transparent conducting oxide is there like uh, um, tin oxide or all those things. And then we have got transparent, this incident light is falling. So we have a glass substrate. And here is like cadmium sulfide and cadmium telluride. So this is the actual area of the semiconductor. And then we have the gold contact. So the contact is between our transparent conductive oxide and the gold contact. So here is a better like cadmium telluride solar cell is there. Here you can see its structure. This is the cross section. So SNO2, tin oxide layer doped with fluorine is the transparent contact that provides current collection from the front side. So we have a glass and then SNO2 doped with fluorine is there and its thickness is just 200 to 500 nanometer. Then a thin film solar cell, the front contact needs a very high transmission. So it should be very highly transparent and high band gap like 3 eV used as a transparent contact on the top cell. Now cadmium sulfide layer serves as the window layer. We have a cadmium sulfide. The heart of the cell is the cadmium telluride layer, which serves as the absorber for the incident. So cadmium telluride we have got and which is around 2 to 8 micron. So this is the actual layer where the solar photon will be falling and we have got this electron hole pair will be formed here. And this is the p-type and cadmium sulfide is the n-type. Then we have got the antimony telluride layer produces an ohmic contact on the cadmium telluride. So because the hole we have to collect the hole from this side and we have to collect the electrons from this side. So we should have a ohmic contact with the cadmium telluride. So Sb2T3 layer is deposited. And then molybdenum decreases the series resistivity of the back contact. So molybdenum around 1 micron thickness is what is this question someone is asking? Crystalline silicon is in SiO2 form or SiO? Crystalline silicon is silicon, right? I am not getting your question. So once I complete this, we can discuss whatever problems are there. So we have the thickness of the cadmium sulfide layer can strongly affect the device performance because if it becomes very thick, so then the light transmission will decrease. So the thin N layer, N-type semiconductor has to be very thin. The cell with a cadmium sulfide layer of 60 nanometer has an open voltage circuit, lower open circuit voltage. So very thin layer is used. So this is a thin film. Now we come to the third generation solar cell. So that was a typical second generation solar cell. Now coming to the third generation solar cells. So these are the organic solar cells or the dye sensitized solar cell or the perovskite or quantum dot. So here we are using organic semiconductors, and or we can be using organic inorganic hybrid kind of semiconductors. Both can be using. So what are the advantages of this organic semiconductors? So first thing is that cost is very less. They are good absorbers of light because we can tune their band gap. So their band gaps are tunable, so they can absorb more and more photons. So more and more electron hole pair can be generated, and this will lead to the formation of more current. So efficiency will increase. Then easy processing because they are organic materials, so very easy to deposit in form of thin films. Flexibility is there, so we can make this kind of flexible solar panels can be made, which can be put into any device, like you can put it on your car or any other places, and convert the energy. Can cover large surface area cost effectively because they are low cost. Then these are organic semiconductors are generally biodegradable molecule and therefore eco-friendly. Now, come to we will be discussing among the third generation organic solar cell, the dye sensitized perovskite and the quantum dot. Very briefly, I will be telling you how they are made. So the basic structure always remains the same. We have a back contact, we have a front contact. The front contact is so as to more and more photons can pass through it. Then we have after the front contact there will be a n type semiconductor, then we have a p type semiconductor. N type will be very thin, and then back contact can be itself can be the substrate, or you require a substrate and metallization. So the organic solar cell is like we have a cathode, we have the transparent conductive oxide, which is the back contact, acceptor layer, and the donor layer. So this is the N type and the P type. So these are the, now we have our organic molecules or uh, organic solar cells. So this is like organic molecules, or they can be some kind of polymers. So indium tin oxide or fluorine doped tin oxide, they are used as the transparent conductive oxide. Now active low layer like the donor and the acceptor. So in the donor P type, we can use molecules like P3HT, or different methyl phthalocyanines are there like copper phthalocyanine, or we have got different PPV or P dot SS, all those polymers can be used. And for the N type acceptors, pyrrolines, fullerenes, fullerene derivatives are used. Then we have this electron transport layer and hole transport layer. So we require, because direct metallization cannot be done, because we have to make a ohmic contact. So for the transport of hole, so above the N-type semiconductor, you require a hole electron transport layer, and at the uh, in the p-type semiconductor, you require a hole transport layer. So these are the different material like p dot pss is there, lithium fluoride, zinc doped tin oxide. These are used for the electron transport as and the hole transport layer. So these are all thin films, and the back contact we take from aluminum or things like that. So this is basically we are replacing cadmium telluride or silicon by different organic materials. So going a bit higher up in the architecture, dye sensitized solar cells were used, have been used. So DSSC. So they also have this three parts. So we have got anode and counter electrode. That is, the two electrodes are there. Then we have an electrolyte, and we have got transparent conductive oxide is there, ITO glass. Indium transparent conductive oxide is there on both sides, and they are also acting as the electrode. So we have got electrode film layer TiO2. So this is the TiO2, which is covered by a dye molecule. So it is covered by these are the dye molecules. So basically the photon interaction is by the dye. So these dye molecules absorb the solar energy. And then we have a electrolyte. So an indium tin oxide layer is used to facilitate charge transfer from the layer, the electrode layer. So TiO2 is the electrode layer and it is coated by dye and then it is in contact with the ITO glass. The counter electrode layer is made of carbon. So we have this counter electrode and iodine electrolyte or some kind of electrolyte is used to supply electrons to dye to replace the one being extracted. So dye will absorb the photon and how it is working, the dye will the light strikes the dye molecule and if the photon has enough energy, it will excite an electron from the dye which is transmitted into the conduction band of the TiO2. So this electron will go to the TiO2. The electron will be connected by the front electrode and supplied to external circuit to the counter electrode. The counter electrode will return the electron from the external circuit back to the cycling current in the cell. The original state of the dye is subsequently restored by electron transferred from the redox electrolyte. So that's why we require an electrolyte here. So basically the dye is capturing the photon, it is giving out electron. Electron is now taken by TiO2 and it is from the front electrode, it is in the external circuit and the counter electrode, it is returned back through the counter electrode and given to the electrolyte. And this electrolyte again supplies back the electron to the dye. So this is how the full dye sensitized solar cell works. So basically the dye is sensitizing the absorption of the photon and the dye can be tuned for different region, color and the wavelength and that's why and it is more efficient. So that's why this architecture has been very popular. Now coming to the other kind of the third generation solar cell is the perovskite solar cell. So perovskite is basically a crystal structure. So perovskite compound has got this ABX3. So ABX3 kind of compound has got this. No? So here A is this, B is one, both are cations. A and B are cations. So A and B and we have got an anion. So X3, this is the X. So where A and B, so their size are very different. And X is an anion that binds to both. So X is bounded to both A and B. So A and B can be both inorganic cation like we have got cesium copper iodide is there or cesium lead iodide, lead bromide kind of thing. So these are all perovskite. So it can be both inorganic cation or one of them can be organic molecule. So they are called, when one of them is an organic molecule, it is called a hybrid perovskite. So materials are like cesium lead iodide is a inorganic perovskite and in hybrid is like methyl ammonium lead iodide can be used. So this is. So band gap is around 1.55. So you can tune. So what kind of combination you are using in this perovskite, you can tune the band gap. And X is a halide in this case. So the advantage is that these semiconductors have excellent optoelectronic properties. Means the band gap is tunable and it absorbs the photon very. The absorption coefficient of photon for this material is very good and very high light absorption and also radiative losses is less. Low non-radiative carrier recombination rate means whatever electron holes are produced, so they non-radiative carrier recombination means they don't recombine to give within the molecule or within the structure, they don't recombine, so that there is no loss of electron and hole pair. And excellent charge transport. So diffusion length is very large. So if there is any electron hole pair which is formed in this part, so they travel long distance before getting recombined. So you will be able that the efficiency of your solar cell will increase. Low crystallization temperature, therefore the fabrication process is easy. Simple method of manufacturing from solution like spin, inkjet printing, spray printing. They can be made into flexible and materials like carbon, nitrogen, hydrogen, lead. So this can be used. So highly abundant materials are used and their efficiency is also very large, like 20%. So this is like a planar perovskite. So this perovskite is there where your photon will interact and electron hole pair will be taken, will be produced, and we have a electron transport layer and hole transport layer. So it can be like electron transport layer can be a fullerene and hole transport layer can be P dot PSS kind of polymer. And so whenever the photon is coming, so electron hole pair is produced within the perovskite. So here you are not requiring a N type and a P type differently. The same perovskite can be used. And then you have got a ITO, no, transparent conductive oxide as a substrate, and counter electrode of silver or carbon or aluminium. And now lastly coming to the quantum dot solar cells. So this is also one of the kind of third generation solar cells. So here we are using the quantum dots. So quantum dots can be of TiO2, or it can be cadmium sulfide or cadmium selenide. So quantum dots are like nanocrystals are there and they are put into some kind of polymers, organic semiconductor polymer. So photoelectrodes, this electrodes like TiO2. So quantum dot arrays or superlattices are there. And then nanocrystalline TiO2 sensitized quantum dots we can have, and it's immersed in a polymer bed. So we have got, so electron and hole, this polymers will be generated. So electrons of quantum dots are excited by the solar energy absorption, and then this electron transfers from the quantum dot to the our transparent conducting oxide via the our TiO2 layer is there, ITO contacts. We have got the TiO2 layer and nanocrystals are there. And then electrons get to the counter electrode after working at external load. So we have aluminium contact, then nanocrystals, which are hole conducting with a hole conducting polymer. Then we have got electron conducting polymer and the ITO contact. And then glass is there as a covering. So the photon will be falling on this nanocrystal, electron hole pair will be generated. Then the polymer hole conducting will conduct the holes and the electron conducting polymer will conduct the electrons, and then the circuit will be completed. So basically whether we are talking about the dye sensitized or the perovskite or the quantum dot solar cells, so these materials are the material, these are the heart of the solar cell. So we are changing the heart, means we are changing the material which is acting as the absorber. If you remember in the first slide we read that there are the absorber is the most important part of a solar cell. So different kind of absorber we can use, and then there has to be an electron and hole carrier within the solar cell. So the electron and hole carrier we can earlier we were using like silicon. So silicon was both doing both the things together. It was absorbing the photon, giving out electron hole pair, and also conducting the electron hole pair. But in these cases, when we are going to the third generation, so we are using a electron transport layer and a hole transport layer. So the transport layer is different than the absorber. So transport layer we are using like a fullerene or a polymer, or like TiO2 is one of them, or an electrolyte. So that is how the architecture is changing, but basic working remains the same. So because of variety of materials and variety of these polymers and how we can tailor their properties, the efficiency of the solar cell can be increased. But then we have to look for their long-term testing, how they can, whether they can be like for solar cell, we are putting them in the open atmosphere. So, and there will be like high temperature, or there can be rainfall, there can be humidity. So, before testing any material, we also have to see just not their efficiency, but how degradation happens and how much time they can work. So this is basically this our this comes to the end of our lecture for the um, functional materials part 2. So this was my last lecture. Now you can tell me if you are having any doubts. So whatever questions was coming, please let me know. So there is one question in the chat box that in multicrystalline silicon, whether Si is in SiO2 form or Si. So obviously the question is multicrystalline silicon. No? So if it is a multicrystalline silicon, it is silicon. It is not SiO2. Otherwise, we would be saying that SiO2. SiO2 is just a passivation layer. And if you remember that we have shown you that whole flow chart. So obviously SiO2 layer is there, which is around 20 nanometer, 30 nanometer thick, coated on silicon or multicrystalline silicon. So you are using both. Single crystal silicon is also used for making the photovoltaic cells, and multicrystalline is also made. Okay. And first question, someone has asked, repeat the first question. The first question was, what kind of wavelength we require, right, for any given material. And second question was, any question from your side?
No, ma'am. Ma'am, what wavelength is required for?
For a good material to be used for photovoltaic cell.
Okay.
Any other problem?
No, ma'am.
Okay. So there will be assignments also, because there will be Viva and I will be giving. So already I have given few assignments. They will be also considered for evaluation purpose. And there will be few more assignment questions which you will get in your mail very shortly. Huh? With next week I will be sharing them with you, which you have to submit. So the duration also I will let you know. So that will be from all my 6 lectures. Okay then. If there is no other question, then I will log out, and wishing you all the best for your exams. And if you need to know anything from me, or you want to discuss any point, or you have got any confusion, you can mail me. We can discuss further. Okay? Okay, bye. Take care.